is there in the midterm examination, and a little bit on, let's say, the various kinds of machine learning problems like regression, classification, clustering, and what are the difference between the three. That is something that, apart from whatever we discussed, is something that you should also focus on. And I hope that is also clear. So from today, we are going to discuss about classification, the next important um, machine learning problem that we typically handle. And again, we'll take some data set. It's again a data set of CT scanner. By the way, Bosch, does it manufacture health equipments? No. Are you in the in the area of health equipments like CT scanner or not? Yes,
Not the big ones, which is like life critical, but
okay,
more of small devices which are for
okay,
diagnosis and for
okay,
evaluation. For example, um, the blood checkup tools and things like that,
Eye
which
okay,
are
testing.
not life critical ones.
okay. And I think you are also in washing machine, right?
Yeah, that's more
Home
of home
appliances.
appliances, washing machine,
Home appliance.
dishwasher, and so on.
Okay,
Yeah.
that's a big business for you, right? Washing machine, because I know
Yeah,
of
that's
Bosch.
quite a big range of devices are there. I mean,
Uh,
equipments for home
uh,
usage,
uh,
premium as well as mid premium
right,
segment.
right,
Yeah,
right. Yeah, Bosch washing machines are pretty well known in the market. So I think you also sell through IFP, correct?
yeah,
Are
that
you,
was the
arrangement?
previous joint venture. Right now, it's Bosch, Siemens. Bosch and Siemens are co-owned by Bosch. In fact, it's
Okay.
even if it's a Siemens washing machine, it is manufactured by Bosch. It's
Oh,
a
okay.
brand has been purchased by Bosch.
Uh, okay. Yeah, because I think there are some case studies, not exactly case studies, but use cases. I don't know if Bosch is doing it, but some of the washing machines, where industrial washing machines, they are providing washing machine as a service. That means instead of buying washing machine outright, if I'm an industrial washing machine, the railway is buying washing machine. So, companies will provide this washing machine on pay per use basis. And obviously, in order to price the how much you pay for every use, you need to have data about usage. Okay? And that's where the sensor data becomes very important. And also the entire the cost structure or pricing structure is that you only pay the customer, who is in this case usually a big industry, not an individual household. They will pay for use, and in return, the supplier of the washing machine will provide all the maintenance and everything. Okay, so there's no separate cost for that. So obviously for that, it is very important to understand that which machine is likely to fail, and then intervene and do the maintenance and all those things. So this is a model actually that has been taken from Rolls-Royce. So Rolls-Royce had introduced, I think 4 or 5 years back, something called engine as a service. So instead of you buying let's say an aircraft company like a Boeing buying a machine Rolls-Royce engine outright, they will they will pay by the use. Okay, and Rolls-Royce will take care of entire upkeep of the machine, and for that they will require all the sensor data, real-time sensor data. So I think similar kind of thing I've heard of in the washing machine space. I don't industrial washing machine, not the consumer ones. So I don't know whether Bosch is getting into that, but definitely that's one model that companies are looking for, and that requires a heavy usage of Industry 4.0 data and predictive analytics and all. Yeah. Good. So we will go today into the next model, which is the classification model. Classification. Okay. And yesterday, I think some of you were discussing about dimension reduction. I honestly, I could not find any relationship between that. I don't know. I mean, in whichever course that has been taught, probably the context was different, because I don't know the context in which this was taken up. So I don't think I should say right or wrong, but it's just that I could not find the context of dimension reduction with something known as classification or something known as clustering, because the concepts are appear to be very, very different. Okay. So anyway, that's, probably I'll not get into that because I don't know in which context it was spoken in terms of dimension reduction. But leave that aside. What we essentially mean as classification is, unlike, let's say, the case where regression, where we had to predict the continuous data. For example, sales data based on advertisement, or the latest exercise that we did, the mean time between failure, which is a continuous value. In this case, we are not predicting a continuous value. We are predicting a categorical value where we are saying, something is yes or no, or some observation belongs to a particular class. For example, whether a machine is going to fail or not fail. Okay, so these are two classes of data, fail or not fail, instead of finding out, for example, mean time between failure. So this is a binary classification. There can be multi-class classification where I can say, okay, the machine is, is going to fail. The machine is absolutely stable, or the machine is, let's say, doubtful, can fail or cannot fail. So it's a three classes. So it can be multi-class classification. So both these situations are possible. And obviously, the approach is different because here we are not technically predicting any continuous value. Okay, so I'll share with you a data set, and let us work with the data set and also understand the concept as we go along. So I'll just share a data set. By the way, please do install 9. I think a lot of people yesterday said that there are some restrictions. I think it should not be very difficult for you to get the permission, especially if some of the departments have got it. Because as I keep repeating, these are things, unless you do it yourself, it becomes very difficult to appreciate what's going on. Yeah. So please make sure that you get that permission and install 9 in your laptops. Okay, so yes, I'll just have the data set. Just see if you have got this data set, CT scanner failure data. Yes, great. So I'll just first show you the data set. Yeah. So this is the data. As you can see, the data is very similar to the other data that we worked on, which is calculating the mean time between failure. We have the machine ID, then the age of the machine, date since last service, ambient temperature, machine temperature, vibration, radiation, voltage, pressure, and then maybe the machine at the time of measuring this status gave some error code. Okay, we don't know what the error code is. Okay, we don't really need to know, but there is some error code. There are some cases where there are no errors, and there are some cases where there are some error code. Then the usage mode, again, normal, high load, and I think something ideal. Few usage modes are there. Location, and then most importantly, the target or the outcome here is not mean time between failure, but it is a machine status. That means when the particular machine was measured, this machine status was either 0 or 1. 0 means the machine was in good condition. 1 means the machine has failed. Okay. So because we are talking about two specific categorical outcomes, either the machine is in good condition or not failed, and the machine has failed, hence we are calling this a classification problem, because we want to classify the machines into predict, given a set of data, we want to predict whether the machine will be in good condition or is likely to fail. Okay, that's what we are trying to do. Okay, instead of just finding out a number in terms of the total mean time between failure. Okay, is the problem statement clear to everybody?
Yes.
Great. Now there are quite a few methods, but two most popular methods used for classification. One is called logistic regression. The other is called decision tree. Okay. So we'll first see how this can be done with logistic regression. What is the meaning of logistic regression? As you can understand, it should be something similar to regression, but something different. And then decision tree, which is a very different approach. Okay. We'll also discuss that which method is more suitable under which condition. Okay. But as of now, we take this data and apply this using both logistic regression and decision tree methods. Okay. So first, let us understand what is meant by logistic regression. Second. So first, let us understand what was happening when we are doing regression. In regression, what was simple linear regression, what was happening was that we had an outcome, which is y. The outcome was a continuous value, and we have to predict it based on a predictor or a feature, which is x. And we had past data. This is the data-based decision making, not engineering-based decision making. So we had some past data, and we drew a line, or we asked the model to draw a line, which is a best fit line, where the R square should be, let's say, between 0.8 and 0.9. Okay, that's what we did. And this works fine when this y is a continuous value. That means that's the mean time between failure, etc. But in this case, the y is not a continuous value. So in this case, what is happening? In this case, I have two cases, 1 and 0. The y is actually two values. Y is two values, only 1 and 0. 1 means failure and 2 means non-failure. And we are saying that some of the points are lying over here, and some of the points, which are failure cases, are lying over here. So it's not like a continuous value of points. It is either lying towards one side, and there are some are lying towards 0 side. And there can be some values somewhere is lying over here. There can be some value which is non-failure but lying over here. Okay. But broadly, we can understand that if x is high, then there is a possibility that the machine is likely to fail. And if x is low, then we have a possibility that the machine is unlikely to fail. Okay. Visually, we can understand that, but the question is that how do I find the given equation y equal to mx plus c that will help me to predict whether given a particular point, given a particular value of x, given a particular value of x, whether this value will lie on which side. Okay. So I need to find an equation. Now, is everybody clear up to this? Yes or no?
Yes.
Now, if we do a linear regression, like the way we have done in case of regression problem, typically my regression line will probably lie somewhere here. Okay. Because it is y equal to mx plus c, so it will try to find out where the the sum of squares is least, and it will probably find out one such line which is lying somewhere here. Now, what is the problem if I have this line? Will I be able to predict whether the machine is going to fail or not fail if I get this equation? What do you think? Will this equation be sufficient enough for me to predict if the machine is going to fail or not, given a value of x? Yes or no? Will I be able to predict?
No.
No. Because why no?
See, based on this linear regression, there cannot be an in-between value. It is only failure or
Right,
no failure.
right,
So
right.
this regression line doesn't give that clarity.
Right. Regression line doesn't give that clarity, because if this is x, that means my point, if I put this as the x value and I want to know what is the value of y, the regression line will give the value of y somewhere here, which is maybe 1.5 or 1.2. And I don't know what to do with this value 1.2 or 1.5. Okay. On the other hand, if the regression, if the x is somewhere here, it will give a value somewhere here, which is probably this may be 1.2 and this may be minus 0.3. And again, I don't know what to do with minus 0.3. Okay. So because I want a value 1 or 0. Okay. That's the best case scenario. But I'm not getting that value. So I need to transform this line. I cannot take this line as is. I need to apply a transformation. Like in engineering, we have studied different types of transformation, Laplace transformation, Fourier transformation, etc., which is basically transforming a base equation into a different format. Okay. So I need to do this regression, but I need to also transform this y value into some other value so that I have a greater clarity on whether the outcome is 1 or outcome is 0. Now, what kind of transformation I should apply? Now, if we leave the mathematical equation apart and if we just look at visually, what kind of equation will help me to have a better idea where this will either be 1 or 0? Obviously, an equation something like an S shape, something like this. Now, if I am able to transform y into this S-shaped curve, then in majority of the cases, I should be able to get a value very close to 1 or very close to 0. Except a small window of this window where I may not get a very clear answer. But apart from that, I should be able to get a clear answer of whether it is 1 or 0. This part clear, everybody? Yes, no?
Yes, Professor.
Okay. So then what I need is a function z which will transform y into this kind of curve. And this should look like 1 by 1 plus e to the power minus y. So this z is equal to 1 by 1 plus e to the power minus y. Now, this is the logistic regression curve. Because it's a logit function derived from the regression line. And that will give us a much better clarity as to whether a machine is going to fail or not. Is this clear, everybody?
Yes.
However, there is a small problem, or rather two problems. First problem is what to do with these. If I have an x value which is here, okay, what do I, because the x value which is here, which will plot into this, what do I do? Also, while we are saying that this is close to 1, this may not exactly be 1. For example, this may be 0.95 because the sigmoid function is asymptotically merging to 1. It is not that it jumps into one value. It will merge, it will become 1 when x equal to infinity. And it will become 0 when x equal to 0. So it's asymptotically merging into 1. So at any point of time this place, the value actually may not be 1, it may be 0.9. So I need to make an assumption that there will be a cutoff value beyond which I will consider the state to be 1, and below which I will consider the state to be 0. And conventionally, that cutoff value is 0.5. That means if the value of z is greater than 0.5, I will consider the machine to be failing. And if the value is less than 0.5, I will consider the machine to be not failing. Now, why 0.5? Is 0.5 the right cutoff? Or should it be 0.4? Or should it be 0.7? This depends on another very important factor, which we are going to discuss later on. But usually it is fine, and that's the industry standard, that this value, this optimum value where we can put this cutoff is 0.5. And usually that is what is accepted. Okay. Now, this of course means that if the points are here, I am more confident that the machine will fail. And if the points are here, I am more confident the machine will not fail. However, if the point is lying between this green zone, I am not that confident. But nevertheless, since I have to classify it, as 1 or 0. This also means that there is a possibility of some misclassification. For example, this is misclassified because when I have a value of x, the model will predict that this value lying somewhere here, but actually the machine has failed. Whereas this point again will be this point again will be a misclassification because this will the model will predict that the machine is going to fail, whereas the machine is actually has not failed in that particular situation. So in this kind of problems, there is a possibility of misclassification. And the amount of this misclassification is the accuracy of the model. In a regression, we talked about R square. R square is indicating the accuracy of the model. Here, the amount of misclassification is indicating the accuracy or inaccuracy of the model. Okay, is up to this clear? Yes or no? Concept clear? Everybody?
Yes.
Right. Okay. So yeah. So this is the concept behind logistic regression. Just like in case of regression, it can work only with numeric values. logistic regression can also work only with numerical values, because after all, it is a equation. Okay. Now we'll see. So obviously the same concept of one-hot encoding, which applies in case of regression, which we need to do when we have categorical values and we are trying to do a regression line. Same concept will also appear over here. Okay, and similarly the same concept of your normalization will also be applicable here, because this is also fundamentally a regression. Okay. Now, based on this, if I make a statement that any classification problem, as of now we have just done logistic regression, so assume that logistic regression is the only method of classification. We'll see that in other methods of classification, this statement equally holds true or does not hold true. But for the time being, just consider logistic regression. If I make a statement that logistic regression or classification problem is nothing but a modification of a regression. In other words, I'm saying that actually there is nothing called a classification problem. It is also a regression problem. We are just kind of modifying it to look like a classification problem. Would you agree to this statement or will you disagree to this statement? Yes. The statement is a classification problem is essentially a regression problem. There's no fundamental difference between a classification problem and a regression problem. Would you agree to this statement or disagree to this statement?
Every classification problem can be a regression problem, but vice versa is not true.
Vice versa is not true. So why are you saying that every classification problem? I'm not saying can. I'm saying that every classification problem is a regression problem. Is the statement, because when I say can, obviously I'm indicating that there may be some exceptions. So I am saying that without exception, every classification problem, at least whatever you have studied so far in terms of logistic regression, is a regression problem.
If it is a classification just into two categories, the way we are discussing now, then yes, it's a regression problem.
Then it is a regression problem, but in regression, we don't talk about two classes. We talk about continuous outcome value. Then why should it be a regression problem?
Continuous outcome, I mean, if you classify a machine as failed or not failed, then it is a digital classification.
Yes, it's a one.
Right? I mean, there is no continuous outcome.
It's not continuous. Okay, so that means, do you say that classification problem is not a regression problem, fundamentally different from a regression problem?
In other words, problem is a regression problem as long as the classification is only into two categories. Okay, not okay, failed, not failed.
Okay, but if it is three classes, fail, not fail, or probably failing, then it will not be regression problem.
I mean, if it is three or even more, then it will not be a regression problem. So there are different states in which it can exist.
Okay.
And so then it's not a regression anymore.
If there are two states, then it's a regression problem, and if there are more than two states, it's not a regression problem. That's just what you say. If there are two states, why is it okay? So if there are two states, why should it be a regression problem? Because regression problem means that you are having a continuous output, mean time between failure, sales value. It can take any value. But if it is two states, it's not any value. It is two states, 1 or 0. So why should it be a regression problem?
Because you can model that with this equation what we have on the screen, no?
Okay.
So 1 divided by 1 plus e to the power of minus 5. You can model that.
It's a modification of the regression equation. That's why we are saying. Yeah. Anybody else has any view? A classification problem is essentially a regression problem. True or false? That's the statement. Let me answer. The statement is absolutely correct. Because what is the outcome of a classification problem? At least from logistic regression, and we'll see later on for all other models like decision tree, naive Bayes, any other k nearest neighbor. These are some of the other models that are typically used for classification. Not always that popular. Decision tree and logistic regression are the most popular. So whatever model we use, all classification problems are essentially a modification of the regression problem. Why? Because what is the real output? What is the value of Z that you are getting? The value of Z is nothing but a probability, which is a continuous value between 0 and 1. Z gives you a probability of the machine failing. It doesn't give you whether the machine is going to fail or not fail. It just gives you a probability 0.6, 0.9. Okay, this value may be 0.6. Okay, this value may be 0.4. This value may be 0.001. This value may be 0.9. This value may be 0.957. So essentially, it is Z. The value of Z is the probability between 0 to 1, which is a continuous value. Continuous value. Just that this continuous value is scaled between 0 and 1. Unlike in case of regression, it is not scaled. It can be any value. But here the value is scaled between 0 and 1. But ultimately, the raw output is a probability. We are imposing an artificial cutoff. This is an artificial cutoff. And we are imposing an artificial cutoff and then converting this continuous value into a categorical value, saying that any value that is more than 0.5 will automatically classify as 1. And any value that is less than 0.5 will classify as 0. But the real value, real outcome is not 1 or 0. The real outcome is a probability between 0 and 1. Am I making sense? Yes, no? Yes or no? Everybody is quiet. Not sure I can repeat, but I need to know whether it's clear or not.
Can you repeat, sir?
Yeah, sure, no problem. What we are saying is that in a classification problem, what is output? Output is Z. What value Z can take? Will Z take a value of 0 and 1? No, the value of Z is any value between 0 and 1 because it's nothing but a probability of machine failing. Because it is any value between 0 and 1, it is as much continuous as a regression output. Except the fact there is a boundary because the probability has been normalized to be between 0 and 1. The range of values has been compressed between 0 and 1, but the value, the real, the raw value output is not only 0 or only 1. It is 0.995, 0.001, 0.672, like that. Clear? How am I converting this to a categorical value of 1 and 0? By forcing a cutoff. That is a manually forced cutoff. That I am saying that any value that is more than 0.5, I will consider it to be 1. And any value that is less than 0.5, I will consider it to be 0. So I'm manually forcing it it is not automatically the output is 0 and 1. And why am I putting at 0.5? We'll talk about that. Why not 3.3 or 0.7? But it is a manually imposed cutoff value. Greater than that value, I'll putting every value of Z as 1, and below that cutoff value, I'm putting every value of Z to be 0. Clear?
Yes, sir.
Correct. Now, other question is, what do you think, again from visually, lower the band, lower this green band, higher or lower will be the accuracy? Accuracy of model. If this band is lower, what do I mean by that? Let's say I have another model where the model fits like this, red line. So this band is now higher. This band is higher. So which model is which line is a better fit, the green line or the red line?
The green line.
Green line. Okay. Why the green line? Because there are more number of cases which are either close to 0 or close to for the green line. Lesser ambiguity. Whereas in the red line, there are many cases which are 0.5, 0.3, 0.7 like that. There are less number of cases which are very close to 1, let's say 0.9 and above, and very less number of cases which is very close to 0, let's say 0.01 and below. So lower this band, higher is the accuracy. What is mean by accuracy? Accuracy is the right classification. Where the predicted class has been accurately classified. That means if it is a failure, it is classifying as failure. If it is a non-failure, it is classifying as non-failure. Not like these two cases, which are misclassifications. So lower this band in the sigmoid, the S, the curved part of the S. Narrower it is, higher is the, or let me call it narrower instead of lower, narrower, higher is the accuracy of the model. Concept clear, everybody?
Yes, but what is the x-axis in this case?
X-axis is the attribute, okay, which is predicting Y. Let's say vibration.
But there are several other attributes, right? I mean,
Yes, so
the influence of all
yeah, that's true for any other. So that means the X, it is not one dimensional, it's multi-dimensional. There'll be another X over here in this dimension. X2 will be here, X3 will be here. Okay. Obviously, we cannot draw these dimensions in a 2 by 2, two-dimensional space.
So it is not a curve, it is a surface.
It is a surface, yes, absolutely. Absolutely. Because we can't draw that in a two-dimensional space. Hence, to understand this is true for regression also. Regression, what did we draw? We drew a simple linear regression, a simple polynomial regression. We never drew a multiple linear regression or multiple polynomial regression because we cannot represent that in two-dimensional space. But in reality, when you're building a model, most of the cases you will have multiple attributes and you will have the curvature in a space, not the curvature in a two-dimensional space. Correct?
I mean, why can't it be a physics-based model? I mean, this is now just a data-based model, and we just plot the data and then we predict it.
So this is the old question that we have gone into. It definitely can be a physics-based model. What did we discuss? That when can we use a physics-based model and when we cannot use a physics-based model? When I know that I know all the input parameters and I know exactly what is the physics equation that is controlling the output, then obviously I don't need any database model. I'll go for a physics-based model. But the problem is in real scenario, in many times, you do not know what is the exact equation. You know that there is some impact of ambient temperature on the machine's failure, but I don't know what is that equation. Yeah, or it is very difficult to formulate that equation. Just like the example that we said that if we drop a pen, okay, the physics-based equation says V equal to U plus Ft, and I can measure the velocity at which the pen is going to hit the floor. But if I measure the velocity, is the velocity same as what the physics model suggests? The answer is no. Why? There are many other factors that is affecting the velocity. For example, any wind movement, any moisture, any surface friction, etc., etc. While I may know those factors, I do not know the exact equation, or it's very difficult to formulate the exact equation as to how the surface, okay, if I use, the wind fluid dynamics and all, in spite of doing all sophisticated fluid dynamics, I'm still not able to arrive at the final equation that will define what is the effect of the wind movement on the velocity, or if there are any other factor apart from this. So you apply database model when you are not, you know that the physics-based model is not accurate because of the limitation of either or not knowing the exact equation or not being able to measure the, let's say the wind velocity or the surface friction. That is the fundamental principle when you should use a physics-based. That's why I asked you this question, that when as a business user, you are deciding that which problem should be given to your data science team, are you able to first figure out that is this problem solvable by physics-based model or engineering-based model or not? If it is solvable by engineering-based model, then there's no need to go for a machine learning-based. Sometimes it's difficult to figure out, is it solvable or not? So you do both and you figure out that which one is giving you better results. Clear?
Yep.
So that's one of the, as I said, that in terms of, let's say what kind of interlock the business user has on with the data science team, this is one of the key areas of interaction. That the decision to go for a engineering-based model to determine when the machine is going to fail or not versus the decision to go for a database model. That is the key. Right now, I'm not sure, but many organizations don't take that, don't go through that process at all. Either they go purely on engineering-based model or they go purely on data without evaluating which of these models are better. Okay.
Yep.
Right. Okay, so now I think that is the theory portion of it. Now we'll see how we can implement this using KNIME. Again, we'll do it in KNIME and then we'll do it in Colab. Okay, whichever is suitable for you, you can adopt that. Second. Just KNIME is opening up. So those of you who have KNIME installed can also open up KNIME. A minute to open up. It's taking a little bit of time. Some of the steps will be common, so you should be able to tell me the common steps. And we will, of course, get to a point where the steps will be different compared to what we did in linear regression. Okay, so here we are. Everybody is able to see my screen? Yes. Yes or no? Everybody is fine, able to see my screen?
Yes.
Okay. So in the folder, we are going to create a new workflow and we are calling this CT scanner predicting failure. Okay. So what is the first step? First step is now should be cakewalk for you because questions also will come on these steps. So by now it should be in your mind, etched in your mind. Yes.
Excel reader, right?
Excel reader, very right, absolutely. If it is by if it is a CSV file, remember you have to use a CSV reader. Okay,
Yes.
because this will be
Yeah,
I have not
right.
given you. Yes. So also remember that when I give you the project, the group project, you have to create this workflow. You can use KNIME or you can use Colab Notebook. Anyone is acceptable. Okay, whichever is comfortable with you. So we will pick up the file. Yes. Are you able to see the pop-up? Where it is, I'm reading the file. Yes. See, already a file specified. 1 second. Did I take the, oh, I by mistake to the Excel writer, okay, which is, yeah. That's why it was saying that because it's the opposite. It was trying to write an Excel file and you're saying that this file already exists. Okay, so it will overwrite the file. Okay, so it has read the file. Okay. Now, one of the things that you have to do, very important, is in the transformation. Now, this output of 1 and 0, do you think it is a numeric value or it is a categorical value? It should be treated as a numeric value or it should be treated as a categorical value.
1 and 0 equal to yes or no, right? I mean, it's
1 or 0 is equal to yes or no, absolutely. So it's just a categorical value and a cardinal categorical value. There is no order as such. Okay, we are not saying that, you know, machine failing is lower than machine not failing, or something like that. These are two categories. There is no order in these two categories. It's just that instead of saying yes or no, the data could have been yes or no, but usually what happens when it comes on the sensors, the data comes in the form of ones and zeros. Okay, so that's why it remains as ones and zeros, not as yes or no. Okay, but essentially this 1 and 0 are categorical values. Okay, so remember in a this in a classification problem, the outcome is always categorical. Can be binary, it can be multiple, but it always will be categorical, can never be numeric. The model will not work if this is numeric. Because it understands the output is a categorical value, it's not a numeric value. Yeah. So far, yes or no?
Yes, yes.
Okay. But obviously, as of now, 9 doesn't know. Okay, at least it's not able to guess the purpose for which we are going to use this. So it has read it as number. Because it sees 1 and sees 0 and it thinks it's number. So we must change this to a string. Okay. So this is one very important transformation that needs to be done, which we did not need to do typically in the joystick regression. Though in case of joystick regression also, sometimes we have seen that numeric values are wrongly read, but that is, it has been read wrongly. But here we can't say it has been read wrongly. It is 1 and 0, so it is thought that it's numbered. But given the context is not a number, it's a string. So we must change this. Okay. And we can check if other things are fine. Machine ID is string, which is fine. Age of the machine and days since last service is a number, which is fine. Ambient temperature, machine temperature, vibration, radiation, voltage fluctuation, pressure bar. Okay, these are all double. That means it's a decimal number. Error code, usage mode, location type. These are all strings, which is absolutely right. So rest of the things are correct. We apply this, say OK, and execute this. We have the data over here.
Sir, the previous window was not visible. I think there was something which was overlaying on top of it.
Which one was not visible? The configuration.
The column type was there, right, in the transformation.
Yeah, yes. Yes.
Yeah, I think we see something on. Okay, this help menu, preference menu is being seen. Maybe if you can just pull the window to left or right.
Yeah.
Dialog 3.1, 3:1.
Is it visible now?
Okay, machine state. Okay, doesn't matter. What needs to be set for? Okay, instead of integer, it should be string.
Status, machine status should be string.
Right. Okay.
Machine status should be string. That's it. Okay. So you have to just change that to string. Okay. Everything else is clear? Okay, great. So also, as we saw in case of linear regression, also we got some statistical values, like are there any missing data? What is the, in case of numeric values, what is the minimum? What is the maximum? What is the Q1? What is Q2? What is Q3? Mean, okay, standard deviation, etc. All So this basically kind of helps you to see how the data is distributed. Okay, is there any skewness, etc. Okay. As of now, we probably will leave it as it is. In a real scenario, probably you need to do a deeper analysis and see if the standard deviation is too high and all those things. But for here, as of now, we can ignore that. Okay. Can anybody tell me what is the next step? Till now, it is the same as that of regression. So when it becomes different, I'll tell you. So if I go by the method for regression, what is the next step? By now, this should be again in your mind quickly. Yes. You need to filter out something.
Machine ID.
Machine ID. Why do you need to filter out machine ID?
Because it's all unique number and it will change the model.
That's right. That's right. But the technical term is?
It influences
high cardinality. High cardinality feature. Okay. Make sure you mention these technical terms in your answer. Okay. High card, because the question may not be on specific to a data set because it's not a practical exam. So it's a theoretical exam. So it may just talk about, okay, tell me the steps. So there you cannot give an example of machine ID. Okay, so here you have to say that wherever there are high cardinality values, you can say example like some IDs of machines, etc. Then those may need to be filtered out because whenever you have a high cardinality value, it is futile to find a relationship between that value and the outcome. And if you are forcing the machine to find the relationship, so in this case, you're forcing a machine to find a relationship, then it is likely that the algorithm will lead to or hallucinate the relationship. So you are forcing the model to find the relationship when there is no relationship. So it will hallucinate a relationship. That is why I should filter out the high cardinality values like machine ID. It can be something as I was mentioning, that it could also be location. Suppose the location itself was maybe specific town or even specific location in the shop floor. And let's say each machine has a unique location in the shop floor. Then also it becomes a very high cardinality value. Yes, so any high cardinality value should be removed. Okay, clear everybody? Yes or no?
Yeah.
So we'll use a column filter. No difference from what we did, and we will take out machine ID. Over here, apply, execute, and we have now data without machine ID. Okay. You would notice that we still have, or rather, the algorithm has generated something called row ID. It was not there in the original data. What is this row ID for? What is the row ID for? The row ID is the primary key of the table. What is the meaning of a primary key? Primary key means that one particular value of an attribute that uniquely identifies a row. And that is essential for any database system to work. When we imported the data, name automatically assigned a primary key to the dataset because we have not told specifically if there is any primary key. There is an option in the configuration where you can say that the machine ID is a primary key. In that case, it would have taken at primary key, but we ourselves may not be sure because in order to figure out that machine ID is primary key or not, we have to scan the entire data and ensure that there are no two rows which have the same machine ID. And usually that's not a very good way because this is externally generated data, especially if it is a machine generated data, there's a possibility of duplicate rows, duplicate values. So it is always better to generate a new primary key. Okay. If machine ID was a primary key, we would not have need to remove it. Also, primary key is never a predictor. That's why you will see that whenever we are trying to find out the columns, here you see that row ID is never in these columns. The row ID will not be considered as a feature. By definition, a primary key is not considered as a feature because primary key is a high dimensionality, high cardinality value. So every row has a different primary key. Clear? Yes or no? All good?
All good, all good.
Great. So tell me the next step. The broad next step that we typically do. And within that broad next step, we do some minor steps.
Exploratory data
Yes,
analysis.
very good. Exploratory data analysis. Very good. It's exactly what you write in your exam. Exploratory data analysis. So we want to find out more about the data, usually visually, so that we can treat the data and make it suitable for a machine learning model to learn. For example, we might need to find out the outliers. We might need to find out the correlation between the various parameters, features, etc. So some of the common exploratory data analysis tools are box plot to identify outliers. So let's do a box plot. Same as that of regression, no difference. So I think we have done a box plot for room temperature, for MBA machine temperature. Let's do it for vibration level this time. Ideally, I should do a box plot for everything. So this is a box plot for vibration levels. I'll not open a new window because there's always a problem in terms of closing the window. But here we can see in vibration level, there is no outliers. Okay. So ideally, I should do a box plot for all the different numeric values that I have to identify any outlier. If there is an outlier, the best possible treatment of an outlier data is always remove the rows. Okay. Okay. Yes. Any questions? Great. Okay. So what is the next thing? The next EDA that we typically do? What is the next EDA that we typically do? And now this should be absolutely in your head, especially for next week's exam. Correlation matrix, isn't it? Yes or no? Yes. And the purpose of finding out correlation matrix is to identify if there are measures that are correlated with each other. Why? Because if there are measures that are correlated with each other, these measures will dominate the outcome over other measures which are not correlated with each other. And in such cases, we have to treat such measures separately. For example, we may decide to take only one of these features, not both. Okay. And sometimes we may also do dimensionality reduction, where we combine two measures into one single variable. Okay. So we need to find out the correlation. Correlation obviously we'll find out only with numeric values. And in this case, in regression also, you never find a correlation between a feature and the outcome. So that's what the regression equation is supposed to do. And here, anyway, you cannot do it because the outcome is a categorical value, not a numeric value. Apart from that, all the numeric features that you have, you find out a correlation. Okay. Yes. Here. Run this. And we see the correlation matrix. Correlation matrix is like this. It's a symmetric diagonal matrix where the value in the diagonal is always 1 because it indicates correlation of a feature with itself, which is always 1. Apart from that, it is the correlation matrix between correlation value between two measures, because it's a combination, not a permutation. So it is symmetric. So whatever is there below the diagonal will be same as above the diagonal. Clear? Yes or no? For example, days since last service seems to have a negative correlation with ambient temperature. That means if the ambient temperature is lower, the date since last service is higher, which kind of conceptually we understand, because if the ambient temperature is lower, probably the machine is working in a better condition, in better ambient situation, and hence it requires lesser servicing. Correct? Yes or no? Everybody clear so far? All good? Yes or no?
All good.
Yeah, yeah.
Okay. Now my question to you is that if the correlation, how do I know the correlation value is high or low enough to treat two correlated features? When can I say the correlation value is high enough between two features that warrants a treatment?
P-value we need to do.
P-value, very good. So these things are something that has to be etched in your mind. P-value. So can we elaborate this a little further? What are we going to look at in the p-value?
If it is lesser than 0.05, it is having a high correlation.
So if the so we have to first say that p-value accepts or rejects a null hypothesis. If the p-value is less than 0.05, 0.05 is just the convention. There is no scientific rule that defines this 0.05. It's just the convention. If the p-value is less than 5%, we reject the null hypothesis. Obviously, the question comes that what is the null hypothesis in this case? Can anybody formulate the null hypothesis in this case? If we take, for example, days since last service and ambient temperature, what will be the null hypothesis? The null hypothesis is that Sorry?
No, days and ambient temperature are not correlated.
Not correlated. Absolutely right. That's the null hypothesis. Null hypothesis is that days is last service and ambient temperature are not correlated. And
one doubt here.
Yes.
Instead of p-value, correlation value itself is an indication, sir. For example,
no.
+1.
Yeah, so but then how do I know? See, I have a correlation value here. Let's say, which one should I say? Let's say radiation temperature, age of the machine 0.023. Okay, and you have another one 0.07. Now, can I say 0.074 is high enough to say that age of the machine and machine temperature are correlated?
No, it should approach +1 or -1 if it is approaching. Like 0.9.
That approaching, the definition of approaching itself is kind of is subjective, right? Because here you can see that there is probably no value which is close to +9 or -0.9.
Yes.
So that means, should I say that there's no features which are correlated? The answer is no, because if I go to the correlation matrix, I have to see, is there a p-value which is less than 0.05? Okay. Most are more than 0.05, which means that but you have this less than 0.05. Radiation leakage and pressure bar, where the correlation value is 0.149. Yes, it's high compared to others. But how do I know this is high enough? 0.149. I mean, on a scale of -1 to +1 is actually not very high. It's 0.1, 0.14. It's not 0.8.
Okay.
But the p-value clearly indicates that it is much less than 5%. So there is a definite correlation.
Okay.
That is the purpose.
Yeah.
That is the purpose of p-value. Because without p-value, we cannot determine what is the value of correlation where we can say that these two variables are correlated with each other.
Understood.
Great. Okay, so ideally I should treat this, but again, as I said, we will not treat this here. It becomes slightly complicated. Later on, if time permits, we'll see how this can be treated. Okay, and how this can be considered when you are actually, and whether, most importantly, after treatment, you have to see whether the accuracy of the model increases or not. It is not necessary that after treatment, the accuracy of the model will increase, because there is something called combinatorial effect. Two factors combined having an effect. So it's possible that, let's say, if you remove one of the factors, it is actually the accuracy of the model is going down rather than going up. Okay. So these are the kind of, you can say, pre-processing or iterations that you have to do while you are doing this modeling. And as I said that, again, if you talk about the interaction between business user and the IT team, ideally this kind of prototype should be done by the business user. Because business user will only identify that is there a case for data science or using machine learning to do this kind of work, or the data is not sufficient, or let's say a physics-based model, engineering-based model is far superior. This kind of decision has to be taken by the engineering team. Once the engineering team is sure that yes, we need a machine learning model and the data that we have is good enough to build a good machine learning model, then it is passed on to the data science team to further work on it and make it more robust, okay, and scale it up for millions of data. So that's why this prototyping should ideally be done by the business team and not the data science team. Okay. So let us go ahead. So linear correlation, fine. So assuming that we don't do anything on the outliers and we don't do anything on the correlation, we just observed it. What is the next step that we should do?
One-hot coding.
One-hot encoding. Very good. By now, I think some of you have really got the thing right. Okay. So we'll do one-to-many. The node for one-hot encoding is one-to-many. But I expect that everybody should be equally comfortable. Maybe some of you are quiet, but I'm assuming that all of you have by now understood all these steps. And not only understood it, it is just, got into your mind. As we can see that one-hot encoding will be done only for categorical values. And we also see that one-hot encoding, we don't want to do a one-hot encoding for machine status because that is what we are going to predict. But we want to do one-hot encoding for error code, usage mode, and location type. Okay, so far fine. One too many, one-hot encoding. And we should see the data over here where the values have been converted into columns. So error code has been converted into 4 or 3 error codes as columns. None, E01, E02, E03. Okay, similarly, location also has been converted to columns. Urban, semi-urban, rural, and normal, high load, ideal has also been converted into column. Okay, so we have successfully converted the categorical values into numeric values using one-hot encoding. We must not directly use values of 0, 1, 2, etc. because then we are converting a cardinal categorical value into a numeric value which has an inherent ordinality, okay, which will be incorrect. After this, what should we do?
Normalizing.
So
before normalization, we need to filter out. We don't, now that we have already one-hot encoded data, we don't need the original data of error code, usage mode, and location. Because if these data remain, we still will have some categorical values as features in the equation, which we don't want. Okay, so we must filter out the original categorical values. Okay, so we'll filter out original categorical values, column filter. So you want which one? Error code, usage mode, and location type. These are the 3 original categorical values we don't want now because we have already one-hot encoded those values. So other values are fine. Must ensure that we have not, we have the machine status there. Yes, machine status is there. Okay, great. What is the next step?
Error code machine.
Sorry?
No, Bhavani.
Not able to hear you.
Partitioning the data?
Partitioning the data. But this time we have to do the partitioning slightly differently compared to regression. Do you remember what sampling we did in case of partitioning when we did regression?
70-30.
Sorry? No,
70-30.
70-30 is the ratio of the 2 samples.
Training and testing.
Huh?
We did for training and testing.
That's right. But these are the use of the 2 samples. Essentially, we are creating sampling. 2 samples. Random sampling. Okay. Now, we cannot use random sampling in this case. So let us understand this scenario clearly. Okay. Why we cannot use random sampling in case of a classification problem? In case of so what does random sampling mean? Random sampling means that I know that I have to take 70% of the data in sample 1, 30% of the data in sample 2. I don't care which 70% is in sample 1, which 30% is in sample 2. Okay. It has to be randomly chosen. And that's how I desire it to be. But can it work the same way in case of classification problem? Okay. First of all, let's assume that if I have two cases, machine failure, and my data is 100 units, there is a case of non-failure, which is 0, and there's a case of failure, which is 1. Let's say out of 100 population, the data that we have collected, 80 is non-failure and 20 is failure. We'll come to something called an imbalanced data set also. We'll come to that. But for the time being, assume that is 80-20. 80 is non-failure and 20 is failure. Okay. Now, when I am dividing this into training and testing data set, and I'm assuming a 70-30 ratio, 70 should be in training and 30 should be testing. Within the training and testing, there'll be non-failure cases and there'll be failure cases. Can I allow the sampling procedure to sample in such a way that the training data set has 70 non-failure cases and 0 failure cases, and the testing case has 10 non-failure cases and 20 failure cases? Remember that number will still be 80 over here, non-failure, and 20 over here, failure, which is same as this. But can I, like in case of a random sample, can I do it like this? Or can I allow the sampling procedure to have in the training data set 70 non-failure and 0 failure, and the testing data set 10 non-failure and 20 failure? Numbers will still match. 70-30 will match. 70, this is 30, and this number will also match. Can I allow this to happen? Yes or no?
No.
No. Why not?
Training should be with the failure also.
So first of all, the training data set has not seen any case of failure. Not only seen any case of failure, if it was 65 and 5, that also should have not be good enough, because then there'll be 2 less number of failure cases. Suppose you're 65 and 5, and this was, let's say, 65 and 5, and this was, let's say, 15 and 15, that also would not have been correct. Right? Because there are 2 less failure cases in the training data set and testing data set. If it was the other way around also, like if it was something like all failure cases 20 here, okay, 50 here, and 0 here, and let's say 20 here, then also let's say 30 here, then also it would be incorrect. What will be the ideal condition? How the samples should look like? How should be the distribution of non-failure and failure cases in training and non-failure and failure cases in testing?
Ideally, 70-30 is okay.
They are also not 70-30, 80-20 in the ratio of population. 70-30 is the distribution of sample. 80-20 is a distribution of two classes in the population. In my sample, the two classes should be represented in the same ratio, or at least in closely to the same ratio as it is present in the population. This is the population. In the population, 80% is non-failure, 20%. So when I draw a 70% sample of that, this must represent the two classes in the same ratio as the population. So how many should be non-failure cases?
20.
Sorry?
56.
56. Absolutely right. 80% of 70 and 20% of 70, 14. And similarly here, 80% of 30, 24 should be failure cases, and 20% of 30, that is 6, should be non-failure cases. All the numbers will still match. This type of sampling is called stratified sampling. When I'm using classification problem, I have to use stratified sampling methodology, not random sampling methodology. This is one big difference in the way you split the training and testing dataset. Is the concept clear?
Yes, sir.
Right. Now, a little bit of digression from here, nothing to do as such with sampling, but let us assume that our data set was where we had 98 cases which is non-failure and 2 cases which is failure. What would have happened?
It is acceptable limits. So
no, it's not acceptable because one of the classes is very rare. This kind of data is called an imbalanced data set. If your data set is imbalanced, you cannot work with a classification problem. There's another very important thing that a business user must check. That when I'm giving the data set, is it an imbalanced data set? Imbalanced data set, of course, this is something that even the technical team can also check. But before it goes to a technical team, this is very easy for the business user to check that the data that I have is an imbalanced data set, and I cannot build a model, a good model with this imbalanced data set. The solution is obviously simple. One solution is that we get more data about failures.
but how we'll come to know about this failure and non-failure in the beginning, sir?
Failure and non-failure to be?
In the beginning of the analysis.
Yeah, so because you are collecting past data with already any supervised learning, you are working based on a data which is known to you. That means you have already collected the data where the machine has failed.
Okay.
Okay, if you don't have that data, you will not be able to do any supervised learning. Supervised learning assumes that you already have data about past failures.
Okay.
And the corresponding, when the machine has failed, what has been the vibration, what has been the temperature, etc. So that's why we always say that, applying machine learning is there has to be a plan. I cannot just say tomorrow I am going to apply machine learning for predicting a failure of my washing machine. No. If I think that has to be this something that we have to take as a project, from now itself, I have to collect the data that is that is required to train the model. And that data collection itself may take 5 years. Suppose I don't have that data. I may have data separately. I may have data about vibration, temperature, etc. But I don't have the data that when the vibration was this much, whether the machine failed or not failed. So if I don't have that data, even if I have only vibration data and temperature data, I can do an EDA. I can just make a scatter plot or something like that to visualize what happened and the vibration and the temperature, what is the relationship, but I cannot build a machine learning model. And if my plan is to use a database model, again, that decision also has to be taken that whether I should go for a physics-based model or a database model. And suppose I figure out that there is a case for a database model, I need to prepare first the data, and probably it may take 3 to 5 years to collect sufficient data. And only then I can start that project. So that is where the strategic planning comes in. Okay, that is where the business user and the technical team has to sit together, do the strategic planning before they can think of building a use case for machine learning. Okay.
I mean, in 3 to 5 years, the technology will change so much. The machines themselves might be outdated.
Possible,
so if we
possible.
Start collecting the data today.
Yeah.
Then after 5 years, we may not be able to use the data.
You may not be using the same machine. Absolutely right. So what is the other solution? The other solution is that if I don't have enough data, we call it artificial data injection. We generate artificial data. And today with generative AI, it is very easy to generate artificial data. Those are the strategies, right? So if I know that
if a machine is trained on artificial data and then it is let's say that model is put to use in a real data, and if the prediction is what is the accuracy of prediction that we can expect?
You are already testing that.
Training data is artificial.
No. So you already test. Okay, what are the things that you do? Okay, you first do a training, then you do a testing, then you do a validation. There are multiple steps. It's not the training and testing and you deploy. The entire model deployment is a separate project altogether. So in the model deployment, what do? I deploy the model in a real life scenario, but I don't take a decision based on what the model is saying. I figure out whether whatever I'm doing right now, maybe physics based or other, I still do that. And I figure out that is the model predicting right in the current situation. Then I start. So there are various steps. It's not that I build a model and I just deploy it. And then within that, you will rightly say that there is something called data drift. Data is changing. There's a model drift. You might figure out that there is a certain set of other features that have not been considered. So that is where the business user comes in. That the business user figures out that during the validation, the model worked very well during training, model worked very well during testing, but it's failing during validation. The model is perfectly fine. Where is the problem? One problem is the data might have drifted. Another problem is the model has drifted. That means there are 2-3 other features which has not been considered, which should have been considered. Go back to the drawing board. We rebuild the model, retest the model, revalidate the model. So it is not that you do once and you can implement it. That is only for academic purpose. Okay. In the academic world, you can just learn one name and then fine. But in real world, it's a very, very different thing. Learning in academics and actually doing it. And you are all practitioners, you know that. Okay. Knowing something in classroom and doing it is very, very different. Okay. So those are the things that need to be done. Okay. But that's again a very, very like model deployment is a very, very different. Also remember the infrastructure that you need. Right now we're talking about 1,000 data. So when you are talking about really training a model, we're talking about millions of data, if not more than that. Where do I store that data? I cannot just upload the data in Excel file. I have to have a data lake. Okay, I have to have a data factory to transform that data. So all of those things have to be in stream. Okay, in line to do this entire thing. And these are all projects. And all these projects require heavy involvement of business user. It cannot be done only by IT. Okay, does it satisfy the question? Yes, no?
Yes.
Okay. By the way, generative AI is big time into this space. Because you can understand if Gen AI can create images and create videos so perfect that it looks like original. Gen AI today has a capability to generate data that is very close to original. So this is where what you exactly say, that what probably would have required 5 years to collect the data, and by the time I collect the data, the machine is already obsolete. That cycle time of product innovation is essentially a product innovation, right? I'm building a model, I'm building a product, and I required 5 years to build a model. That has reduced to 6 months or even less. Okay. So this is where in the product innovation space, generative AI is playing a big role. Okay, so we're talking about analytics for competitive advantage. This is analytics for competitive advantage, where you are able to use generative AI to generate synthetic data, and you become ahead of competition because they have not been able to use it. Okay, all good, guys? Shall we proceed? Yes, no? But very good
Yes, sir.
questions. And what I want, I mean, we have some, what I want, that's why I keep repeating this, that if you are applying this in your work, and if you need any kind of suggestions, please do not hesitate, because I am also interested in knowing how you are applying this in your real business and what are the challenges that you are facing. So that is the real, otherwise just doing this theoretically, learning few formula and few stuff actually doesn't help you as practitioners. You are not a fresher doing an MBA graduate, MBA degree. For them, it is fine. For you, the application is very, very important. You have to figure out that what are the challenges, not for this course only, for any other course that you are learning, what is the challenge that you are facing if you have to apply that knowledge in your business, or even before which knowledge is applicable in your business, which knowledge is not applicable for your business. So first that filtering, that this knowledge is fine for theory, great, maybe it is applicable in some other industry. For my industry, it doesn't have any use. So that's one level of filter. Okay, for passing out the exam, I'll study, but it has no application. Second level of filtering is that, okay, these things which I've learned are probably applicable in my business. Let me see what are the challenges that I may face if I have to apply this in my business. Okay. So second part is what I'm interested in. Please feel free to discuss. I'll be very happy to see how you are applying it in your actual business. Okay, great. Let's now go back and do this sampling in So we will do partition. This is, I think, your node is, some of your nodes are slightly different from my node. I have this table partition, and Now here you see the 70-30 still remains same, but we will not select random sampling here. We are going to select stratified sampling, and we have to say that on what basis we want to do the stratified sampling. Okay. That means the sampling should be done in such a way that the ratio of one of the fields, the value of one of the fields should be the same in the sample as in the population. And what is that field? The field is the outcome field, which is, or the target field, which is the machine status. Okay, it has correctly identified this, but if it's not identified this, you can just manually put it. Okay, in most of the cases, probably it will be able to identify it itself. Okay, so and we know the purpose of random seed. The purpose of random seed is to ensure that for my workflow, for your workflow will be different. For my workflow, every time I run the workflow, the same set of observations will be in the training data set and in the testing data set. Okay. Otherwise, what will happen that every time there will be a new set of observations in the training and testing, both following the same rule, that 70-30 as well as in the ratio of the population, but the individual observation may be different. As a result, the model will be different. Okay. So we'll keep it as random seed and apply and execute. And what we see that there are two partitions or two samples that have been formed. The first partition has 337 rows, and the second partition has 145 rows. In the first, one way to find out whether these partitions, how many 0 and 1 cases are there, we can first find out total how many 0 and 1 cases are there. Okay, so we can do a pie chart. So we are finding out how many total 0 and 1 cases are there, and we want to do this for machine status. We want to do it for occurrence count. Yeah. So this is a very balanced data set. You can see 50% is 1 and 50% is 0. Okay, probably it is a super clean data set that has been taken. But even if it, let's say 60-40 or 70-30, it is considered to be a balanced data set. Okay, beyond that, it might be imbalanced a little bit. And now after table partitioning, I want to know whether the first partition, what is the ratio of 1 and 0? Take that, machine status, occurrence count. Okay. Yes, 0, 1 is 50%. And we can take for the other one, the test data set, 0, 1. Status, occurrence count. Yes. So you see that it has been able to do the stratified sampling correctly. So far correct? Yes or no? All good?
Yes, here again this failure and non-failure we are able to see, sir.
Failure and not failure?
That maybe separation or classification of the same population ratio.
Yes, yes, yes. So it is the same. So both in the training and test data set, it is considered as 50-50. Okay, so you can see that in the two samples, the failure non-failure ratio is maintained the same ratio as the population.
Okay.
Correct. Now, one thing is important that we really don't know which one is failure and which one is non-failure. Okay, so we have to assume. Okay, we have to assume. Let's say we assume that 1 is failure and 0 is non-failure. Okay, something
Okay.
like that. Okay.
Okay.
So that's obviously whoever is business user is owning the data, that business user knows that 1 means failure and 0 means non-failure, but we don't know. We are just assuming. Okay. But it's
Okay.
important to know to be consistent in our assumption. So if we say 1 is failure and 0 is non-failure, we have to analyze everything considering that. Okay. So okay, great. So now next step is learner. So this time, last time is a regression learner. This time is logistic regression learner. Logistic regression learner will learn from the training data set. Okay. Now, here you can see it is saying what is the target column, which one you want to predict, and what is the reference category. This reference category is very important because later on when we will assess the misclassification, this will be, and some of the metrics, this will be based on what we have defined as a reference category. So in this case, we define reference category as 1, which means that 1 we have taken as failure. So failure is a reference category and non-failure is the other category. So we have to remember this because other calculations will be based on what we have defined in the reference category. If the reference category changes, we can change that. If the reference category changes, make it 0, then the calculations also will accordingly change and the interpretation of the calculations will also change. Okay. For now, let us assume that we have taken failure, which is 0, as the reference category. Okay. Did we do normalization or did we forget that? Oops. Okay. We forgot that. Okay. So we have to use normalization.
Professor, can you repeat the logistic regression once?
Yes, I'll do that. But before that, just let me normalize because normalization is without normalization, we should not proceed. Okay, we missed that step of normalization. Okay, so we'll do a min-max normalization and so min-max normalization will normalize everything. Yes, all the numeric values. So machine status is a non-numeric value, so automatically it is not a part of normalization. We'll execute this and we have the normalized data. And this normalized data will now get into the table partition.
Is mandatory to normalize all the fields?
Mandatory to normalize all the
fields.
Regression, logistic, yeah, so all the fields anyway has become numeric now, right? Except the output. Except the output, everything else is numeric, correct?
Okay. So is it mandatory, sir? Otherwise, we can choose the fields.
No, it is mandatory to normalize all the numeric fields because that's the purpose of normalization. Otherwise, certain fields will dominate. The other certain features will dominate the other feature.
Okay. Maybe it maybe depends on a business case. Maybe if that is a fact.
No. There's no business case here. There's absolutely no business case. This only this is pure science. That if my equation is y equal to m1 x1 plus m2 x2, I cannot have x1 dominate over x2.
Okay.
All are equally important parameters.
Okay.
So I have to normalize. Now the method of normalization may vary. That's a different thing. I can use a Z-score normalization or some other form of normalization. But I have, in a regression situation, I have to mandatorily normalize all the features, but not normalize the outcome. Features have to be normalized.
Okay.
So, okay. Now, yeah. So you're talking about regression. So take the logistic regression learner. And in the logistic regression learner, what we have to say, what is the target column machine status? What is the reference column? Later on, we'll understand the use of reference column, that one of the values, 1 and 0, one of these values we have to consider as reference because the model's accuracy and few other parameters will be calculated based on what has been defined as reference. If I define something else as reference, then the calculations will change. Okay, so we can take any one of them as reference. Okay, that's fine. But whatever we take as reference, we must consider all other calculations based on reference. And obviously, we are considering all the values as my input. Okay, and there's something called stochastic gradient. We'll ignore this for the time being. This is to do with how you are optimizing the model, but we can ignore this from a business perspective. Okay, this is good enough. Is everybody clear so far? Yes?
Yes, sir.
Apply and execute. So my model is created. My model is nothing but an equation. This time it is not a simple equation, the simple regression. It is a logistic regression. And that equation now I'm going to apply on the predictor. Logistic regression predictor. The model goes over here and the data on which I'm going to test, which is a test data set, goes over here. It's like the student entering an examination hall. The student is served the question paper. Okay, the student is the data and the question paper is the model, and the student is asked to write the answer. The answer is the prediction. Okay, so what do I do over here? We say that what is the column where I'll store the predicted value. So I can, by default, the name is prediction machine status. If I want, it's just cosmetic. If I just want to give a better name, I can just say predicted machine status. Now remember, we say that any classification problem is essentially a regression problem in the sense that the output is always a probability, and we are giving a cutoff of 0.5 to classify into 1 and 0. The real output is not 1 and 0. The real output is a value between 0 and 1. Now, if I want to know that probability value, I can just say append columns with predicted probabilities. That means along with classification, classifying it as 1 or 0, it will also tell me what is the probability that it actually got from the regression, and based on the probability, it classified as 1 or 0. This part clear, everybody? Yes, no?
Yes, clear, sir. For logistic regression, we call this sampling is stratified, and for linear regression, what is the name, sir?
It was random sampling.
Random sampling. Okay.
Random. Yeah. Okay. So once we run this, we have the output. Here you see that the output is 0, 0, 0, etc. Okay, some 1, some 0, and you'll see that this is not necessarily the same as the actual output, actual actual machine status. So is the actual, like you see, the second one is 1, 0, 1. Okay, and this one is actually quite a few zeros and then 1. So it is not matching with the 0 and 1 as observed in the test data. This is the misclassification. So we need to figure out how many such misclassifications there and which type of misclassification. There can be 2 types. Okay, the machine has failed, but I have classified it as not failed, or the machine has not failed and I have classified it as failed. It is very similar to type 1, type 2 error. Some of you who are in quality know. The same concept applies over here. How many misclassifications are there, and that indicates the accuracy of the model. But there are a few other parameters which I think we'll take up in the next session, where we're going to measure the accuracy. Also, you can see that the probability is 0.897. So probability of machine status being 0 which we are assuming to be not failure, is 0.897. Probability that it will be one mechanism one that is will fail is 0.103 for the first case, and hence it is classifying as 0 because the probability is greater than 0.5. Anything that is greater than 0.5, it is classifying as non-failure, and anything that is less than 0.5, it is classifying as failure. Okay. So far, fine, everybody?
Regression predictor.
Yes, sir.
Great. So I think we'll close here. Remember to save the file, those who are working on it. Okay. Save the file and we'll continue with this file in the next session. Okay. But before that, I'm not sure. I think next Saturday, I may or may not have a class. Not sure. If you don't have a class, then we'll see the next. Sorry? Yes. This today, whatever we discussed is not there in your midterm. Okay, so no need to study this for your midterm. But you need to know about the difference between classification and regression, which we have discussed in the beginning of our session, the different types of problems. Okay.
Yes, sir.
Great. So see you then next class. Okay, and next class maybe next week or the week after that, depends on when you do. Depend on whether you have a class next. We have a class next week or not. Okay. And best of luck for your exam. I hope that no more apprehensions about the exam. Okay. Okay.
Thank you, sir. Thank you.
Okay. Okay. Bye. Bye. Have a nice weekend. Bye. See you.